Hello, everyone. My name is Fei Hu at the IBM Center for Open Source Data and AI Technology. Today, I will give a talk about a distributed deep learning approach for the mitosis detection from big medical image. Before my talk, I will give a brief introduction about our center. The mission of our center is to make AI solution easier to create, deploy, and manage for the enterprise. And our work in our center focuses on the open source, big data, and AI technology, including the Apache Spark, Arrow, TensorFlow, Cloud, and Jupyter Enterprise, and the Max. This talk comes from the Max project, which is a place for the end user to find and share open source deep learning model. What I will go over today, first I will introduce the motivation of this project and review the related work. Then I will give details about our approach, and then introduce the performance of the model and introduce how to use the model in the Max. Motivation. So this project wants to answer a question that where the mitoses are located in the high resolution stained medical image. And normally it requires a few years of training to get enough knowledge and hands-on experience to answer this question. And even for an experienced expert, it still will take a long time to examine the image. For example, in the right image, the expert need to use the microscope to zoom in the image and examine the slide one by one. But the result may be there may be a big difference in the result given by different experts for same patients. So one experiment shows that for the agreement in the for some unformed breast cancer image, the agreement may be as low as 48%. That means that the subjectivity issue is very critical in the mitosis detection. So here we want to utilize deep learning model to automate the mitosis detection process. When we build the model, we want the model to answer the following three questions. The first one is that which area in the image are the background area. So the white area and the pink area in this image are the background. They occupy most area of this image. And the second question is that which spots are the nuclei. And in general, the dark blocks can be the nuclei, and they are widely spread across the image. And they have different size, color, and texture. The third question is that which nuclei are in the phases of mitosis. There are four phases during the development of mitosis. Each phase has different size, shape, location, texture. And the normal cells usually have, many normal cells have very similar appearance with the mitosis. Besides this question, there are also some challenges in the training datasets. The first one is a large area of background area. This kind of data will not help the model training, but will increase a lot the training time and the inference time. Also, compared with number of normal cells in the image, the number of mitosis is very small, and the training data set is also limited. To address this challenge, many research work propose different kind of approach. In general, they can divide into two categories. The first category is use a handcraft feature-based approach. So it uses a computer vision algorithm to detect the dark blobs in the image and manually select the features for the classification model, such as SVM and random forest. And for the second category is the CNN-based approach. In general, they use the convolutional neural network to automatically detect the features from the input image and feed them into the classification layer to detect which part are the mitosis or not. And for this CNN-based approach, it can also be divided into two categories. The first one treats this problem as a classification problem. So it uses the move the sliding window across the image to generate the mitosis candidates, and then use the classification model to classify which candidates are mitosis or not. The second approach treats this problem as an object detection problem. So it first uses a coarse model to propose some mitosis tiles, and then use a more accurate model to identify which candidates are mitosis or not. So in this project, we try both the object and the classification approach. I will give more details in the last section. So in the methodology section, I will introduce the system workflow, model training, and inference. Our approach is a two-stage model. In the first stage, we use the master RCN to propose the candidate patches. So the input will be the original whole slide high-resolution standard image with high resolution around 50,000 by 50,000. So this image is too big to be held by the GPU. So we split them into small region of interest with the size 512 by 512. And then we run the master RCN model on this ROI image to detect the nuclei, no matter the nuclei is in the mitosis stage or not. Then the output will be the polygon, and we use the polygon to generate the candidates as the input for the second stage. The second stage is a classification-based model, and the first step is to add the data augmentation normalization to the mitosis candidates. Then we run the classification model on this candidates and get the predictions probability for each mitosis. Then we search the threshold, probability threshold for each to get the best F1 score. Once we get the threshold, we can know which candidate are mitosis or not. Then we will load the mitosis location in the input image and combine the output from the first stage. The first stage gives the shape information about the nuclei. So with this information, we will derive the shape, size, texture information about the mitosis. Then we can build other model to estimate the tumor proliferation score. Now I will introduce how we train the master RCN model. We use the data from the Kaggle Data Science Bowl 2018, and this training dataset provides a pixel level-based label. So as shown in this figure, this image, so for each nuclei, they provide a polygon to represent the label. And in total, there are about 30,000 training labels for the training image. And this data are varied in cell type, magnification, and image modality, so that we hope the model trained on this data can be general for different kind of case. And in terms of the model architecture, we use the Retraining 50 as the backbone and set the stride size from 4 to 128 to capture the features at multiple scale, and also set the anchor size from 8 to 128 with different ratio of the weight, width, and height, so that the model can detect the nuclei at different sites. This slide shows the proposed tiles by the master RCN model. And the colorful polygon here is detect nuclei from the master SAM model. And we use the center point or the polygon to extract a 64 by 64 patch as the input for the second classification model. And as the right figure shows that the master SAM model can remove the background area, such as the white area. And we also want the model to keep the training dataset labels. So we evaluate this output on the 2-pack 6 training datasets. And we found that it can keep almost about 99.64 of the training datasets. So that means the first model can efficiently remove all the background area, but also keep the training dataset labels. That means can keep the mitosis for the second classification model. So this slide just recaps the data pipeline in the first stage. The input will be the ROI image with 512 by 512, and we run the master SAM model on the image to detect the nuclei, and then generate the mitosis candidates for the second classification model. Here we compare the classification approach and the object detection approach. The upper part shows the classification approach, so it moves the sliding window across the image with the overlap and to generate the candidates. So it will include many background area. And the overlap is added to keep the mitosis on the edge of the sliding window. And for the second step, for the second approach, we can directly propose the mitosis, but don't contain any data about the background area. So this approach, our master SAM model can reduce the mitosis candidate from 3 milli to 0.3 milli, so reduce the data size about 10 times. Once we get the mitosis candidates, we can start train a classification model to see which candidates are mitosis. So we use the data from 3 computation, 2-pack 2016, and ICPR 12 and 14. And take to the 2-pack 2016 as an example, the total data size is about 600 gigabytes, but only 10 gigabytes of them have the label for the mitosis. This label are low the pixel level. They only provide the center point of the mitosis. And the label are annotated by 2 experts to keep the good quality. Before we train the model, we add the augmentation and normalization to the mitosis candidates. And basically, we want to add the noise to the training data sets and also increase the training data size, especially the number of the mitosis data size to avoid the data imbalance issue. We try both VGG and ResLat model, and we also combine these 2 models together in the inference time to increase the inference accuracy. For the loss function, we treat this problem as a binary classification problem. So we use the sigmoid cross entropy as the loss function, and use the Adam as the optimizer. And for the metrics, we record the loss and F1 score, precision, recall, and visualize them in the tensor board. After we get the initial model, one big problem is about the large number of false positive cases. And that's because the normal cells have very similar appearance with mitosis. For me, I couldn't identify the difference between them. So we resample the false positive cases to generate a second set of training data sets and retrain the classification model on these new data sets again to improve the model performance on these hard cases. So this improves the classification model performance a lot. And after we get the prediction result, and some mitoses are very close to each other. And the computation organizer rule requires that if the distance between two true positive prediction is smaller than 30 pixels, then they will treat this one as the same prediction. But if these two predictions are wrong, then they will treat these two as two wrong cases. So we want to cluster the prediction result and to increase F1 score. Here we use dpscan to cluster this prediction. And both the model training and the inference is very time consuming. Oh, not this one. So we want to parallelize this process. And first we develop a GPU manager for this cluster to check which GPU are available in this cluster, because we may run several jobs in the cluster. And once we get the available GPU information, then we split the data into several partitions and assign the data for each GPU. And in the inference period, the approach is very straightforward. So we use Apache Spark to load the model the graph with model weights for each GPU, and run the the data optimization, normalization, inference for inside each GPU. And it can speed up the inference time in linear. But in the model training part, we use TensorFlow on Spark to launch a distributed TensorFlow. And basically, Apache Spark is used to read the data from HDFS and do the data preprocessing. And once finished the data preprocessing, it will do the data shuffling and write this data into a Python queue on each data load. And then the TensorFlow workload will go to fetch the data from the batch from the Python queue and run the training for each iteration. But here there are two issues, performance issues. The first one is the small files in HDFS, and it will be very low I/O efficiency when you read the many small files from HDFS, and also sometimes out of memory on the Spark master load. And the second issue is about the data transferring from Spark to TensorFlow. And for the first issue, we use a workaround solution. So basically, we store all the file paths in a table, CSV table. So store them in the HDFS, and and then use the arrow library to directly read the byte stream from the HDFS and decode them as a tensor in the TensorFlow. And for the second issue, we didn't solve it yet, so we are developing some TensorFlow operation to directly load the data from HDFS into the TensorFlow C++ end, so that avoids the data transferring from TensorFlow, from Spark to TensorFlow. And here shows some inference results. And the object detection approach achieves about 0.6 F1 score, and which is a little better than the classification approach. But the inference time is reduced from 9 hours to around 1 hour. Also, it helps a lot with the hyperparameter searching, because the object detection approach do not need to consider about the overlap between the sliding window. The model I introduced has been published in our model asset exchange project. So Max project is a place for the end user to find and share the deep learning models. And you can build the model service just in seconds. Here example to run the mitosis detection model. So you can either get some Docker image from the Docker Hub, or you can run it locally. So here I will give you a demo how to use that. So here I already downloaded the code here. And the first thing we need to build the Docker image. Okay. Is it clear? Okay, so then you can run it. And here, because I run on my local laptop, then I can just access it. So here is a REST web service, and you can submit the post request here, upload your image, then it will return the result. Which one is? Because on my laptop, you can only run CPU, so it will take some time. And I can also show you a demo notebook in the Jupyter notebook. So here I start Jupyter notebook. Let me start this. So here is the example image with 512 by 512, and here with a link for the REST post. And we can submit the request. I don't know what happened to my laptop, but we can try this public API. So this model also deployed on the IBM cloud. So it will return the mask for each nuclei in the image. And basically, in the demo, I want to show that. Let me restart the Docker on my laptop. So this is the result from our public API. And let me rerun it on my local laptop. So submit the request. Okay. Backend receive the request. Okay, when the program running, do you have any question? So we get the result from our REST API, and we can visualize the result on the image. So basically, this colorful polygon are the location for the detected nuclei. And once we get the detected nuclei, we can input this patch for input the classification model. And the classification model is also available on the IBM cloud. Here you can just load I just load one example here. And you just binary classification, so return the probability for this tile is mitosis or not. Yeah. That's a demo. And all the code are open source and is available at this GitHub repo. And you can also find other projects in our center through this link, GitHub Codate or developer code. And any question? Okay. Data from what? Yeah. Sorry, could you speak a little loudly? Sorry, I couldn't hear.
So my question is, in one of your previous slide, one of the operation you mentioned that you were using data smooth.
Yeah.
So what was the purpose of that operation?
So data smooth basically want to clustering the prediction result because the nuclei are very close to each other, right? And the computation use the size about 30 pixels to evaluate your prediction. So some nuclei are very small than 30 pixels, so we want to combine this kind of prediction result into a single one. So we want to smooth the prediction result. Does that answer your question?
All right, thank you.
On one of your slides, you mentioned there were two issues, and one of them being reading data from TensorFlow, reading data on HDFS from TensorFlow. Could you go a little more into that?
You mean this? You mean this size?
Yeah.
So what's your question?
So one of the issues at the bottom is data transfer from Spark to TensorFlow.
Yeah.
Could you talk a little bit more about that?
So here, at the beginning, we just use the Spark image API to read the data, but we have many small image in the HDFS. So when we read the data, just out of memory on the master Spark master node. So that's because too many metadata information about the file path and the image location, something like that. And then we work around this issue, just save all this small file path in a big table, and split the record to different Spark workload, and use Arrow client to connect the HDFS, and read the stream, a byte stream about the image from HDFS at the byte stream, and decode this byte stream as a NumPy array in the PySpark. Then use the placeholder to transfer the NumPy array from PySpark to TensorFlow C++ backend. That's the workflow currently we have, yeah. But this pipeline is not very efficient, and we have some benchmarking result on that. So we use one GPU to train the model. It will take about 8 hours. We use 2 GPU on different nodes. It will still take about 6 hours. The I/O, it takes a long time. And another issue is that when we reshuffling the data, because reshuffling the data, we need to repeat this data pipeline again. And data shuffling is also not efficient in the PySpark. So yeah, that's our experience. Yeah. Mm-hmm. Any other question? Okay, then, yeah, thank you.